I think it's good to be able to jump on this now because it really relates to what we were just learning, right? So one of the things we were learning is that if I had a situation where, let's see, weights of adult males from 1865 is approximately normally distributed, standard deviation of 30. Standard deviation, sigma, is equal to 30 for that population. You randomly sample 25 men from that population, so our sample size is 25, right? And find that the sample mean is 150. So the mean is 150. Should I call that mu? What should I call that? I'm going to call that x bar, right? Instead of x representing one value, I'm going to call it x bar. That's the sample mean. If I use x bar, if I use SD, I'm talking about a sample. If I use mu or sigma, I'm talking about the population. I don't know what mu is. And in most cases, I'll never know what mu is. I'll never know what the mean weight of all males from 1865 in New York City are. Right? I doubt if. Well, I picked a bad choice. I probably could know that if I really wanted to know that from census. No, actually, it wouldn't be on census information. Right? It wouldn't even be on the health department survey that they do every year because they wouldn't be doing the whole population. So I'll never know that value. I'll never know what that mean is. So I'm dependent on a sample to estimate that mean for me. But what I do know is if I know the standard deviation of that population, I know what the spread is. And if I know what the spread is, I know how those, if I take repeated samples over and over again, I know how they're going to distribute themselves. I know how far apart they're going to be. If I set a limit of 99%, how many what the lowest would be, what the highest would be. I get a good idea of what the range of these things would be within that. If I know what that standard deviation is, we're not going to know that either. I'm going to assume for the moment that we do know that we know that the standard deviation of the population is 30. Okay, if I take a sample of size 25 from this population and the mean comes out to be 100, what did I say, 150? Mean comes out to be 150. Well, that's nice that that's the sample mean. I don't really know if that's the population mean, right? So I say to myself, well, I do know that this is distributed in such a way that if I know the standard deviation, I know basically how these samples, if I took enough of them, would be distributed. But all I know is this pegging point, his starting point is 150. So let me start with that point. I'm going to say to myself, okay, let's start for a moment, assume that that is the population mean. How would samples be distributed if that were the population mean? Well, 95% of the samples would be sample means of size 25 would be 2 standard deviations above and 2 standard deviations below. So if that sample size, if that's 30, sigma is equal to 30, sample size is 20, that means the standard error is equal to 6. So I would expect 95% of the results, if that were really the mean, to be between, say, 12 below this, which would make this 138, and 12 above would make it 162, would be between these two numbers, right? Well, I don't know that that's the sample mean at all. I'm going to use that a slightly different way. I'm going to use that to tell me that that's the point we started from 150. I don't know what the true population mean is, but I think it's likely that the true population mean lies somewhere between 156 and 162, right? How confident am I of that? Well, if this were a sample distribution, a real sample distribution, what percent of the outcomes would we expect to be between 2 standard deviations above and 2 below? 95%. So I'm going to say I'm 95%, based on this result of 150 from this one sample, I'm 95% sure that the true sample mean for the whole population is between these two numbers. And am I 100% sure? No. How about if I want to be 99% sure? Instead of being 2 standard deviations, I would have to be, 99.7, I'd be 3 standard deviations, right? We'll talk about other ranges of this as well. Okay, So depending on how certain I want to be, my range, let's say, how about 90%? If we're willing to be 90% sure that I captured the real true population mean by these range of numbers above and below the value that I got for the mean, would that 90% range be wider or narrower than the 95% range? It'd be narrow. I could afford to be narrower because I'm less confident. If I want to be more confident, I have to be wider, right? So 90%, 95%, 99%, right? My range has to be wider. Okay, so let's look at a way that we might actually calculate this. Okay, so let's see what we have here. So now let's start with our mean from our sample, which is going to be X bar, right? Let's add and subtract from that X bar the standard error times some value which represents the level of confidence that we want to have. So what would that value be that represents the level of confidence? How many standard errors? Well, for 95% confidence, that value is going to be, I'm tempted to say 2, but really what I should say is 1.96, right? Because that represents the range of 2 standard deviation below or 2 standard, but actually really 1.96 standard deviation above and below represent that probability of 95%. So if I wanted to calculate a 95% confidence interval for the mean, I would use a formula. Let me see if I can't undo all of this stuff. Where is he? Get rid of all this junk. I'll abandon all of this. And I would say, let's say, okay, I'm going to use a formula from now on, X bar, my sample mean, plus or minus, I'm going to add or subtract 1.96 standard errors from that mean that I calculate. So if my mean for my sample was 150, plus or minus 1.96 times my standard error. How's my standard error calculated? It's sigma over the square root of n. What was sigma? Sigma was 30. The sample size was 25, so this is 5. So that's equal to 6, 1.96 times 6. So my 95% confidence interval for the true population mean is, and now that I've done the 1.96, I'm gonna wind up calling it 2 and add and subtract 12 just to save a few moments, right? So actually, why not just actually calculate it? Okay, so it's going to be, let me clear my memory, 1.96 times 6. Okay, and now let me ask you something. This number turns out to be, I made it go away, 11.76. Here we go. Just want to be able to get to that quick. That turns out to be plus or minus 11 point, I messed it up. What was it again? 1.96. Is 11.76, right? That's the number I'm going to add and subtract to 150 to give me a range, my confidence range. What's another good name for that? If I told you that the polls right now showed Hillary Clinton with 46% of the vote plus or minus 3%, what would that put? Margin of error. Let's call that the margin of error at 11.76. That standard error times 1.96 is our standard of error. Perfect. Okay, so let's say our standard of error, going to add and subtract that from 150. Right? Every time I touch this thing, it changes. 1.96 times 6. So this I'm going to put it in memory. Clear it. So I'm going to have 150 minus that is going to be, how did that happen? Yeah, I added it twice. I'm on 1.96 times 6. Okay, remember that plus. Okay, play that. 150 minus. Cool. What am I doing? Clear, 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 clear. Okay, I've cleared everything. 1.96 times 6. Okay, I'll put that into memory. Good. Clear the register. 150 minus, call memory. 138.24. Right? And if I add it instead of subtracting it, I'm going to clear this 150 plus my margin of error. It's going to be 161.76. Okay, so what are we saying here? We're saying that we believe that the real mean is between these two values. We're not 100% sure, we're 95% certain. If I want to be more certain, I might want to say this is 95% certainty, right? Confidence interval of 95%. Let's say I want to be 99% certain. Okay, how am I going to use this formula differently to be 99% certain? The standard error is going to stay the same. That's not going to change, right? So what here has to change? This value, the number of the z-score below and above the value that we're starting with. We have to have a wider range. So instead of 1.96, what should we use for 99% certainty? Okay, let's go to our table. I told you should take a break. That does get a little annoying. Okay, so let's see. What should I need? What do I need for a 1% area? Okay, so I'm going to start at the bottom end here because it's just easier to work with. When I'm looking for an area of 99% means I have 0.5% in the lower tail, 0.5% in the upper tail. So what z-score do I need to get 0.5% of area? So I'm going to go through here and I'm going to look for the thing that's closest to 0.005. Well, it looks like it's right here. That looks like actually between these two. I'm going to use this one right here as being closest. What is that? That's negative 2.58. So instead of using 1.96, which would be appropriate for a 95% confidence interval, now I'm going to use 2.56. So when I do this calculation again, what's going to happen? Calculator. When I do this calculation again, I'm going to clear that and clear memory. So it's going to be 2.56 times, 2.56 times standard error of 6. Now, my margin of error now is 15.38. I'm going to put that into my memory. And so 150 minus that margin of error is equal to 134.64. So instead of being 138, now it's 134.64. What about the value on the other side? 150 plus my margin of error. It's going to be 165.36. 165.36. So you have a wider range for your 99% confidence. This is kind of an oversimplification. When we get into the lecture next week, you'll get a somewhat more accurate view of what this really represents in terms of if you had taken, say, what would happen if you took 20 samples, right? And what you would expect with 95% confidence interval is that if you took 20 samples, you would expect 19 of those 20 samples to be within a certain range. Okay? When we get into the lecture next week, we get a little bit more, but from a usage point of view, this is pretty much what we're going to do. What do you think that I'm going to ask you guys to look it up if you have it hand. Actually, you can You can probably get to it online on Blackboard. I'm going to ask you, what would be this number? 1.96 would be for 95%. 2.56 would be for 99%. What number would you use for a 90% confidence interval? Ah, geez, way ahead of me there. Okay, 1.64. How did he get that? You guys, how did he get that? What did he went to the table? Right, he went to the table and he looked for the area that would give you 5% in either tail. Right, and if I go to the table again, right, oops, 5% in either tail would be represented by, let's find the 5%. Closest thing to 5% looks like around here, so it's going to be 1.60123. 1.64, right? And you'd get 95% at the other end at 1.64. 1.601234. There's your 95%. At the other end, because it's measuring the left side. Yes. I don't think so. I think pretty much this is as accurate you really need to be. This is statistics, not rocket science. So I hate to say this, but while Levi's in the room, but it's not really an exact science. Am I wrong to say that? It really isn't. It's the whole point of not being an exact science, because it can't be an exact science, right?
You're saying those two numbers were I did this in 1.05.
Yeah. Oh, I see what could you interpolate? Yes, you could absolutely, if you wanted to interpolate between those two numbers, that would be more accurate. In fact, let's give it a try on Excel. Let's see what Excel gives us for that value. Oops, wrong. Okay, anybody remember what I needed to find a z-score for a p-value for a z-score? What was it? It was norm s dist, right? Parentheses. Now I didn't put the equal sign in. Okay, and what's it asking for now? It's asking for a z-score, right? So actually, what do I want here? I want to find I want the inverse. I don't want this. Equals norm s inverse parentheses. Now I got to put in a probability, right? So our probability could be either negative. A probability is going to be 0.95. Actually, what are we doing it for? 90% or 90%? So it would be 0.95. It would be one tail, right? Parentheses. So this should give me, this should give me the positive end, right? So what's it going to give me? It's going to give me 1.6449. So yeah, that's what you would get. That's your interpolation between the 1.64 and the 1. Whatever was on there, 1.644 and 1.65 or whatever that was on there. So you get a little bit more accurate. In fact, I think, yeah, you can keep going. Remember that formula that we showed you with the exponents, the really nasty formula that we showed you at the beginning, maybe about 2-3 weeks ago, and we said that formula is a representation of the normal distribution, the function that is a normal distribution. You could use it's an integral and it's got a natural logarithm in it. It was very ugly. Let's see if I can't find it. Formula. Okay, so we can get some images here. Here, how about that? You want to work that out? Right? That formula, if you could use that formula to calculate the normal distribution. Or this one. Right? For any mean and standard deviation. Right? That'll give you your probability for each value. For each value there. Each value of x and mu. Right? But that's what that table is built up from. And in fact, if the standard normal distribution, right? What are the values of mu and sigma in this formula for the standard normal distribution? The value of the mean is 0, and the value of the standard deviation is 1. That's why they call it the standard normal distribution. And that's where they get that table from. That table is a combination of those values and this formula. Okay? Now, I have no clue how this formula was derived. Levi, how was this formula derived for the normal distribution? Have you ever seen it derived? You can say no if you haven't. It's got to have something to do with it's a probability function, right? So, I mean, I can't even think of where to begin. I mean, there are some derivations I can figure out, but this one I'm not sure I would know where to begin. I'll have to see. Maybe there's somebody on YouTube that derives it.
Yeah, I mean, there are some very different derivations depending on what assumptions you're starting with.
Hey, listen, it came up, so who knows if there's something there. Here we go. I'll have to turn my speaker on. We may get an echo on.
Income transformed using the logarithm all have this bell-shaped distribution, either spread or thin.
Right?
This is approximated by normal distribution, with Greek letter mu describing its mean, and sigma its degree of spread called standard deviation. But if we try to write down the probability density function, it's actually a monster. It has e, pi, and all jumbled up into a complicated formula. But no worries. Let's go through the derivation of this formula. First, the basic formulation. Second, the coefficient. And third, the details of its exponent.
I'm not sure. You can't see it on.
Imagine you're throwing a dart at a circle board. Given the same distance from the center, the larger areas are more likely to be hit. And given the same area, the closer regions are more likely to be hit. Remember that because it's circular, rotating this shouldn't change anything. But let's just pick some axes x and y. The first step is to explain why the basic formula is the exponent of negative x squared. Pick any point with coordinates x and y. If you consider the probability of a dart landing on this thin vertical strip, that's just fx times the width of the strip delta x. Same logic goes for y. Alternatively, the point can be described by polar coordinate using radius r and gradient theta. If you consider the probability of a dart landing on a square box, that's just some function of r times the area. But hey, this must be the probability of landing on x and y strips at the same time, which can be described by multiplication. Cancelling out the area and differentiating with respect to theta, we get fx dfy d theta plus fy times dfx d theta is just 0. Using the chain rule and polar coordinate representation, we have fx f dash y x plus fy f dash x times negative y must equal 0. Rearranging, we have the f dash x over fx times x must be equal for any point x and y. Well, that's possible only if this value is a constant. Let's focus on x for now. Moving x, integrating. We get that fx equals some constant a times the exponent of x squared times a constant c over 2. Recalling that farther away from the center, the lower the value of fx, we must have that c is negative. Now you see that this is a basic structure. Let's move on to the coefficient a and show that it's equal to 1 over sigma times root 2 pi. Because fx must describe a probability, the integral must equal 1. And because of the symmetric structure, you can just consider half of the domain and say it's 1/2. Moving the constant a, we know the functional form. But the thing is, we can't just integrate this. If we could, we wouldn't need the normal distribution table that's found in almost all textbooks on statistics. So instead, let's consider a joint normal distribution. Introduce y back, put them together, and use polar coordinate instead. Here's where pi comes into play. Using integration by substitution and using a new variable u equals r squared, we have that the left-hand side just becomes minus 1 over c times pi over 2. Well, that's just saying that a is root of negative c over 2 pi. So let's go to the last step describing the relationship between c and sigma. The variance, sigma squared, is defined like this, assuming that the mean is 0. Substituting what we already know about fx and using integration by parts, we see that the formula cleans up very nicely, and with the first part both equal to 0, and second part minus 1 over c times root 2 pi over 2 times root negative c. Well, it turned out that all these complicated things cancel out with a coefficient, leaving c equals negative 1 over sigma squared. Remember earlier when we said that the mean equals 0? Even if mean is not 0, we can slide the axis by mu to adjust it. Putting together, writing c in terms of sigma and shifting the mean by mu, we find the details of the exponent as we originally saw. In summary, the first step described the functional form, the second the coefficient, and the third the exponent. They came from how joint normality implies relevance of proximity but not rotation, and the fact that integral of fx has to equal 1, an adjustment of the mean and the spread. Now you know the derivation of this not so simple function behind so many natural and social phenomena around us.
There you go. So the answer to your question is yeah, if you want to use the formula, you're welcome to, but I'm using the table. Okay, so yeah, you could actually calculate, you could actually use that formula to determine the areas that you need. But nobody's going to do that, right? Okay. Oh no, that area. Yeah, that's true. It does, because it's only giving you the point on the curve. So all you would have, you still have to integrate that to get the area from that part down or up. Yeah. So yeah, you still have to do an integration beyond that formula. You have to integrate that formula from whatever value you start at to whatever. Okay. All right. Let's take a look at the last example that I'm going to give you guys a chance to try. It's on that sheet. And let me display it here. Okay. Okay. Remember the male heads, right? They're still around. Okay. Standard deviation of 1 inch, and you randomly select 100 males and find they have a mean width of 5.9 inches. Calculate the 95% confidence interval for the true mean head width for this population. I'll just repeat up here what we know. We know that the standard deviation is 1 inch. The sample size is 100. And we know that the sample mean was equal to 5.9 inches. Let's calculate the 95% confidence interval. Did we scare you guys away online? Were you able to see that video as we were playing it? And hear it? I should turn my audio down here so that I get an echo. Did it make your head spin? They're still answering yes. I don't know if they're answering if they saw it or made the head spin. A couple of them feeling dizzy. But really, if you had slowed it down, it probably would have been intelligible. It might. You do need to do a little bit of calculus, a little bit of differential calculus. Not a lot. Somebody give me a lower range or an upper range. I think they have a calculator. Okay, let's see what we got. Our first guess was 6.096. I don't need to refer to it as a guess, but 6.096. Well, since that's above 5.9, that's our upper limit, right? What about our lower? Right now we want to subtract the margin of error from 5.9. Anybody got it? 5.704? Okay, let me give it a try. So my confidence interval is going to be x bar plus or minus 1.96 times my standard error, which is 6. Okay, so it's going to be, I'm sorry, it was, yeah, 0.1. I'm still in this last problem, 0.1. So it's going to be 5.9 plus or minus 1, I don't know why this is doing this, 1.96 times 0.1, or in other words, plus or minus 0.196. So let's do this. Calculator. And so let's clear everything. Okay, so 5.9 minus 0.196 is equal to 5.704. That looks good. Okay, let's do it the other way. 5.9 plus 0.196. You guys see how we got the 0.196, right? It's 1.96 times 1/10, so I'm just move the decimal place over. And that gives us our margin of error. And that's going to be equal to our 6.096. So our 95% confidence interval is 5.7 basically to 6.1, okay, for a sample size of 100. Okay, so now if I were to do this for a 99% confidence interval, what would change here? This would be 2.58. And if we were to do it for a 90% confidence interval, this would then become 1.64. Right? Smaller number, smaller margin of errors, narrower range. A higher level of confidence, higher z-score, 2.56, wider range. So we need that wider range in order to be sure that we capture the mean, or be more certain that we capture the mean. We're never sure. We never know. We never wind up knowing, in most cases, what the mean